Good afternoon. Today's afternoon session will be handled by Dr. Alvin Roshan Pais from the Department of Computer Science and Engineering, NIT Surathkal, on the topic cryptography. Dr. Alvin Roshan Pais took his doctorate from the National Institute of Technology, Surathkal, in the year 2014. MTech from the Indian Institute of Technology, Bombay, in the year 2004, and BTech from Mangalore University in 95. His areas of interest include algorithms, complexity analysis, etc. He has carried out so many projects. He was the chief investigator for the Information Security Education and Awareness Project Phase 2 for 2.7 crore rupees. Then the Information Security Education and Awareness Project 2004-2014, again for 1.3 crore. And the development of tool for detection of SQL injection vulnerability in web applications for 33.322 lakhs. In addition to these projects, he has coordinated several other projects also. And he has got more than 18 high quality journal publications and 25 conference publications. And his achievements include National Merit Scholarship Government of India in the year in 89-95, QIP Fellowship, ISCA Travel Fellowship, Best Paper Award ICIP 2010 Bangalore, Best Paper Award Secureware 2011 France, Marcus Who's Who in the year 2011, and the Best Paper Award for the CSI Convention in the year 2011. With this introduction, I would like to invite Dr. Alvin Roshan Pais to handle the present session. Thank you.
Am I audible?
Yes, yes.
Okay.
Yes.
Yes. Thank you very much, sir, for the nice introduction. So there may be some interruptions in between because of the internet. So it looks to be a little bit troublesome. So nevertheless, we will start with the session. So my session is from 2 to 3:30.
Yes, please correct.
Yes,
Yes. There is no voice now.
Yeah, I mean, there is some problem. There is some problem with the internet, looks to be. Because I'm not able to move the screen.
Okay, okay.
Okay, fine. I think now it has come. So outline is we are going to see what is called as one-way functions. What is the necessity of one-way functions? Then two famous relaxations, that is overcoming efficient adversaries with negligible probability. Then we are going to discuss three design principles, that is start, stop, and validate. Then we are going to also see four security paradigms, that is space, time, uncertainty, quantum mechanics, and finally 5 future facets, that is AEIOU factors, that is adversity, exactness, interdisciplinarity, overhead, and unification. These are the things what we are going to cover in today's session. So let us start with some of the simplest things as far as the first thing is concerned, one-way functions. So one-way functions are nothing but the trap. They are designed with trapdoor. That is, one-way function is a function from A to B, which means to say that given an input, you are going to transform into other form wherein it is easy to perform this one-way operation, but the reverse operation is hard. For example for this is you people are using the computers wherein you need to give your login and password. So now the password is not stored as a plain text, rather it is stored as a cryptographic hash output. So you are going to compare this crypto hash value whenever you give the password for the authentication. Hence, in this case, inverting this your one-way hash into plain text is a hard problem. So if you say the complexity theory, it is NP complete. Now, but in the one-way direction from a plain text to the hash output, the operation is very, very easy, which is nothing but it is taking polynomial time. So in one side, it is polynomial time. And if you want to invert it, it is in NPC. So that is the beauty of one-way functions. So they are very, very important as far as our cybersecurity is concerned. For any authentication, we may perform it either by using what you know, that is by means of login and password, or you may do so by means of what you are, that is using your fingerprints or using your iris scan or combination of both of them. Then you may authenticate based on what you have, that is either your credit card, debit card, or any other mechanism of using what you own, that is maybe using your mobile phone itself or using a mobile app along with an OTP, so and so forth. So these are the different authentication techniques what you use, and we are going to have one-way functions being widely used in most of the cases of authentication, simply for the reason that it is computationally efficient and cost effective. If you go for any other mechanism, you have to have more computation and it is a costly affair. Other way around, if you take the case of your fingerprint and iris, if you use it for authentication, you need to have a secure mechanism for storage of this information. As you know that even if you put any sort of security mechanism, this information of your password file is stolen by the adversaries. Since inverting the password from hash to the original plain text is hard, they are finding it hard. But if you are using the mechanism of your iris scan or your fingerprints, then storing these data is very, very important. So how to store it securely is a challenging problem. You may end up with revealing the information if you do not store them correctly. Hence, it becomes difficult. So one-way functions are widely used in current day. They must be used, for example, on today's environment, we are using secure hash algorithm 1 or secure hash algorithm 2 or secure hash algorithm 3. Then, now we have the issue of we are able to authenticate to a system by means of login and password. Now, two people want to communicate with each other. If they want to communicate over an insecure channel, they will reveal the information what they communicate to all other parties who are observing the insecure channel. So any adversary can scan your port and get all the information what you are sending to other parties. party anytime. So now, to perform this task securely, you require what is called as either secret key cryptography or public key cryptography. So in case of secret key or symmetric key cryptography, you are going to use a key for the purpose of encryption and decryption. That is, same key is used by the sender as well as the receiver for the purpose of encryption and decryption respectively. Now the question is, how are these two entities, that is sender and receiver, going to share a common key? The reason being that they are connected over an insecure channel. Whatever Alice sends to Bob is also seen by all other people, including Bob. And the same way, if Bob is sending some information to Alice, that information is seen by all people, including Alice. So now, what is known to Alice and what is known to Bob, when they communicate this information over the insecure channel, the same information will also be known by every other public party or an adversary who is also watching you over the network. Hence, how shall we go about doing the task of sharing a common key? Now the issue is, if we take such a scenario, it is impossible to send a secret information from Alice to Bob, because what is known at time t is equal to 0 to Alice, that is the same thing is known to Bob at t is equal to 0, and same thing is known to everybody else at t is equal to 0. Let us assume that at t is equal to 1, Alice sends some information to Bob. Hence, at t is equal to 1, Bob knows what information being sent by Alice to Bob. And in the same way, all other people, those who are the observers, also will know the same information sent by Alice to Bob. Hence, at t is equal to 1, information known by Bob is equal to information known by every other observer of the network. And vice versa is also true. Suppose now Bob sends some information to Alice, all others, including Alice, will know the information. Hence, if Alice wants to send a secret key to Bob, that secret key will also be known by every observer and adversary who is watching the network, and the vice versa is true. So hence, it is a challenge. So now, to overcome this challenge, we need to do some mechanism of assumptions. So what we mean by these assumptions? So assumptions are based on our complexity theory. If the problem belongs to the class P, we are very happy. We see that the problem can be solved in polynomial time. Now, if suppose a decision problem belongs to the class NP, which implies that it is hard, computationally hard to solve. Now, if at all we have to do the task of sharing a secret with Bob, then Alice must find a mechanism in which the information what Alice sends to Bob will help Bob in solving a problem in polytime, and all other adversaries, even though they got the same the value or information, they will not be able to derive the key in polytime. In the same way, if Bob sends some key information to Alice, now Alice will be able to derive the key based on the trapdoor what is being provided by Bob, but the all other entries or entities will not be able to derive the key. So now the probability that all other people will be able to derive the key should be negligible. So what we mean by saying negligible is it is a negligible function. That means to say Alice and Bob will derive the key in polynomial time, and all others, if suppose I assume the key length, the common shared key length is, let us assume that we want
Hello.
a two, yes,
Hello, Alvin sir.
yeah,
Sir, your presentation is still on outline and introduction page.
correct, that's correct, that's correct,
Okay, okay.
that's correct.
Oh.
So my audio is the audio, am I audible?
Yes, sir, you are audible.
Yes, fine, fine.
Okay.
If I'm not audible, let me know. That means network is gone.
Okay, fine.
Yeah. So now in this case, now the issue is the adversary should have. So let us assume the key size is 256 bits. Then what we mean by negligible probability is that adversary will be able to get the key with probability 1 by 2 power 256, which is negligible. That's what we mean by that. So based on these two relaxations, if we see here, so now if you see impossibility of perfect secret key establishment in insecure channels, if you can see this observation 1 at t time t is equal to 0, whatever the receiver B knows, the eavesdropper C knows 2. Observation 2 is in every subsequent time period, whatever B receives, C receives 2. So now putting the two together, perfectly secure key establishment is impossible. Right. As per this, it is impossible. But now what we do here, let us see in the next slide. So now what we do is relaxation 1. The adversary is a probabilistic polynomial time strategy in the security parameter n. So what I mean by security parameter n, that is the length of the key. That is how many bits. It can be 64-bit, 128-bit, 256 bits or any number of bits based on type of algorithm. Either it is DES algorithm or AES algorithm or any other symmetric key algorithm. Yes. So now adversary must have the chance of getting this key in probabilistic polynomial time. Then the relaxation 2, what we are saying is probability of error is negligible in n. That's what we discussed. Probability of error is mu of n is negligible in n. 1 by 2 power n is negligible. This is what we say. Now, to do this task of securing, the sharing a secret key, we want an adversary is a probabilistic polynomial time and probability of error is negligible. So then how do we achieve this in real life? So now this is, that's the reason why we have what is called as discrete log problem. So we are saying that, let us say in our modular arithmetic, a power x is congruent to b mod m, which means to say that m divides a power x minus b. So now if Alice and Bob are two entities, Alice and Bob have to do the task of having common A. So Alice will initially do a prime value selection P and which will be given to Bob also. So Alice and Bob, both of them will know this value. Now Alice will select a secret value X and he will generate a power X. And he will send this to Bob. Since A is also known to Bob because they have shared A and P are being shared by Alice with Bob, Alice generates A power X mod P. It gives some value Y and Alice will communicate this Y to Bob. In the same way, Bob already has value of A. He will generate some other secret value A power Y and send it to Bob as Z. So both these values are transferred. So all these two values, that is A power X and B power Y, are everybody. And if they have to get back this value of X or Y, it means to say that given A, B and P, that is A power X is congruent to B mod P, in that given A, B and P, their task is to find X. Now finding X, is it easy? It is not so. Because now you have to try all possible cases of X such that P divides A power X minus B. That means to say that you will start with A power 1 minus B. Is it divisible by P? Yes or no, so and so forth. Now typically the value of X is around 256 bits. Now number of attempts an adversary needs to do is 2 power 256, which is billions of attempts. So what is the probability that he will be able to in much lesser time? It depends on whenever you are being asked to design a system with 256 bits, you designed it using, let us say that 100 bits. Now, his computation requirement has exponentially decreased. This is what we mean. So the adversary may be able to get it if suppose you have not used the proper mechanism of selecting the things. And using the discrete log problem, we have what is called as defilement key exchange protocol, which does the task of exchanging the keys securely between any two entities, which can be extended to any number of users straight away. Okay, now we have some examples. If you see one-way functions need for multiple representations of information. Example A is passwords. The machine needs to know your password to authenticate. However, for privacy, it must not know your password. So this is a catch-22 situation. You as a user want to get access to a system. So you put in place a login and password. So now to log into the system, you are supposed to know your password to get access to and authenticate. Other way around, let us think in the other direction. Your password needs to be secure, so it should be private. When you say it is private, which means to say that the password should only be known to yourself and nobody else. But in this case, your computer knows your password. So hence, wherein you are saying in one side, you only need to know and your password is private, and you are giving it to the computer and the computer knows your password, hence your password is not private, which is a catch-22 situation which we need to balance. The next thing, next example, public keys. The receiver knows the key. However, the eavesdropper must not know the key, right? That means to say that if you are using public key crypto system, in case of public key crypto system, you are saying your public key must be known by other party and private key is secure and it is only known by yourself. But the eavesdropper also know the public key because since it is public. However, the eavesdropper must not know the key. That is not going to happen. That is the second observation what we are making. Then x and f of x are two representations. One of them is immediately processed and other is very hard to use. So what does that mean? Yeah. So now what we are saying is that from one-way permutations to pseudo-random generators. If you are saying you are doing a one-way function, what is it going to do? It must be able to do some permutation to pseudo-random generators. So they are used by cryptographic hash functions to generate the hash value. So now we need to have for a symmetric key mechanism pseudo-random generators. There are different ways and means of designing pseudo-random generators. The simple, the one-time pad itself can be used as a pseudo-random generator. Then pseudo-random generators to pseudo-random functions. Because only one pseudo-random generator is not sufficient. So we need pseudo-random generators to pseudo-random functions so that we have a large set of these so that we can use them. That is also required. So now example of this is pseudo-random functions to pseudo-random permutation is the Feastel network, what is being widely used in case of AES and DES, which we are using. And then from pseudo-random permutations to we need to have CPA secure encryption. That is chosen plain text encryption. What do we mean by this? When you do the task of encryption, we need to prove that our encryption is secure under a threat model. So what does that mean? So now you know that in which environment you are using your system. There may be direct threat or indirect threat. For example, it can be an active attack or a passive attack. So for example, to give a example for active attack. So now if Alice and Bob are doing the task of sharing a secret key, what an active attacker can do is he will be the man in the middle. He will collect all the information from Alice, whatever she sends to Bob, and also the man in the middle will also collect all the information what Bob sends to Alice. Now he will give his own information to Bob and his own information to Alice. Now, instead of Alice and Bob generating a common key, in this case, adversary and Alice will have a common key, and Bob and adversary will also have a common key. Now, what he has done is that since Alice and Bob did not authenticate each other before going ahead with sharing a key, the Alice does not know with whom she is communicating, and Bob also doesn't know with whom Bob is communicating. So an adversary in the middle, that is the man in the middle, has taken advantage of this, and he is actively pursuing an attack by giving the information what he wants to be given to Alice and Bob to generate a common key, so that he will also get a key. So this is what is meant by the active attack. So now in case of passive attack, so now what you do is that any information flowing between Alice and Bob, you will not alter. You will only observe and store. For example, Alice is sending the password to the server because logging in, Alice is logging in to a server. So now the adversary will capture all that information, what is going from Alice to the server. He is never going to change anything, what is being sent by Alice to the server. But what he'll do is, from the information he gets, what he stores, he tries to design or get or derive either the plain text or the key. So this is the passive attack. So now man in the middle can perform either active attack or passive attack. In case of active attack, he changes the content what is being received from the other party before he sends to the next party. In case of passive attack, he doesn't change any information what he has received from any party. He passes it on as it is without any modification. But he saves a copy of the same and tries to derive the key or plain text. So now, and chosen plain text attacks secure encryption, which means to say that you are choosing the plain text now, and you are providing this to the system which does the encryption, and you are trying to see whether can you find some relation with either deriving a key or the ciphertext. So now what you do is you are generating a lookup table rather. You know, for example, you know some of the weakest keys, you know some of the common messages being shared or sent by the users. So what you do is that you in advance encrypt the message using the algorithm, either AES or DS, using the keys what you know. So now what you have done, you have taken a plain text, you have randomly chosen a key, and you have done the task of generating the corresponding ciphertext. So now what you do is that you know some plain text, your system you want to break is something which you want to attack on, you will simply give your plain text now straight away. Now, if this plain text, when you give, it gives a ciphertext as output, and if the ciphertext matches with whatever lookup table you have generated in advance, you have got a key within no time. So this type of attacks will become most of the time successful if, as a designer, you make major errors in selecting a key. That means to say, you are selecting a very, very weak key for your encryption. So then CPS secure encryption has to be proved. That means to say your algorithm, you need to prove that it is CPS secure. Such a thing will not happen. Then we need to see that from chosen plain text attack security to chosen plain text attack security to chosen cipher text attack. So now encryption. So encrypt, then authenticate. So what we are saying is that first you encrypt the message, then authenticate, not before. So even the authentication you are encrypting, then you are generating a message authentication code for the entire encrypted message using a key K dash, and which is being sent. The other party will do the task of decrypting the things, checking the messages, then comparing the message authentication code to see that it has come from you. So which can be done. So now our question is, do one-way functions exist? The answer is not known. The reason is, it says that one direction is easy, say in class P. The other cannot be harder than the class NP. So now what we are saying is that in one direction it is P, other direction the same problem should be in NP. So but if P is equal to NP, then both directions are easy. Then one-way functions cannot exist. That is the analysis what we are saying. Because we do not know whether P is equal to NP as far as complexity theory is concerned. We are assuming that P is not equal to NP, but there is no theorem or there is no proof that P is not equal to NP or P is equal to NP. Hence, we cannot say whether there exist one-way functions. So if you design a simple one-way function, it may so happen that the inverse operation is possible in polytime. So the adversary may be able to break your one-way functions easily. So now popularly conjectured candidates are for one-way functions are discrete logarithm problem, what we discussed, then the integer factorization problem. It is nothing but given a composite number n, the task is to find its prime factors. As per the famous theorem of arithmetic, what we are saying is that given any number, it is possible to represent as factors of powers of primes. That means to say, if you have a composite number, you can represent as factors of powers of prime. So now the RSA is based on what is called as integer factorization. That is, you will disclose n, which is a product of two prime numbers. And now if the adversary wants to break your system, he needs to get these two prime numbers from the composite number n. So why it is such a hard problem? Because it is assumed that integer factorization is hard. So now if your input number n, let us assume that it is 512 number. Now any adversary, if he wants to break, now he has to find at least one prime number which will divide this number n. Okay. Now if he has to find this number, that means to say n is 512 bit, then your number p, which is prime, will be 2 raised to the power 256 bits. So you need to find a 2 raised to the power 256 bit number which will divide this. Again, we have the Euler's theorem, which states that number of primes are infinite. That means to say the prime numbers are finite. You can keep on doing it till infinity, still you will find the prime numbers. What we do not know is whether the prime numbers appear as some pattern. That is not known. That means to say, if you start from the initial natural numbers, I have the first prime number being 2, then 3, 5, 7, 11, 13, so on and so forth. Which means to say that in the beginning, we have the frequency of these prime numbers is much large. So the number of prime numbers between 1 and 100 is not equal to number of prime numbers between 101 to 200. So which means to say that there is no fixed pattern with which these prime numbers. So as this number, your number series increases, then you are supposed to know how many numbers of primes are there. If you ask a question, there is no answer, since number of primes is infinite. But there is one more result which states that if you randomly check 116 numbers, you are bound to get at least one prime. That means to say, given a range A to B, if you simply select straight away 116 numbers, you pick them, you are going to get at least one prime number. So that means to say that with a frequency of 116 numbers, you are going to get at least one prime. Now you have to have, if you assume that 2 raised to the 256 is a number which you have to select, now you can see that how many such numbers are there. 2 raised to the 256 is billions of numbers. Even though you are able to get one prime number, now you have millions of prime numbers of size 256 bits. Now, if you start doing this task using your computer, first you need to have sufficient memory to store these prime numbers. Hence, it becomes infeasible for you to do this task. So that's why we say, yes, integer factorization is hard. The next thing, what we need to do in cryptographic design are foundation definitions. Why we need is very simple, because we need to know when we have to start our design and when we have to stop. So what we are saying is that formulation of exact definitions. This specifies the stop condition of design process. Then second thing is reliance on precise assumptions. This is where the design starts. And the third principle is rigorous proofs of security. Cryptographic solutions must be accompanied by a proof that mathematically guarantees its security with respect to the definition and assumptions. So what do we mean by this? So what we are discussing here is that now how do you design a cryptographic system? Because you have given a problem. In the current scenario, if you see, Government of India only encourages the digital mode of actions, or everything they want it to be digital. They have the Digital India initiative. In the same way, they have cyber security program. Then they have integrated cyber physical system program, so and so forth. So the emphasis of the government is only to go digital. So now when you do this task in digital form, you need to see that whichever this system you design, it is secure. So now to say that, you need to know so many aspects of the problem. That means to say, where is this solution deployed? Who are the users? What are the number of users accessing it? Is the solution scalable? Is the scalability required? Then what should be the level of security? What I mean by level of security is that, does the algorithm require 64-bit key? Does the system require 256-bit key? Does the system require 512-bit key? Now, if you say that your system requires 256-bit key for encryption and decryption, and you are designing, and on the other way you are saying that such a system will be used as a mobile app over a smartphone, then your entire system is going to collapse, because the operations by your mobile on a 256-bit encryption and decryption are going to consume lot of power, so which will lead to the shutdown of your mobile phone within short period of time. Hence, now the next, that means to say that now the device itself has become a very, very weak link in your entire system design. So it has made what even though you have designed a crypto system with good algorithm, your entire system has failed only because of the reason that the battery power what you have with your mobile will be consumed very fast, hence leading to denial of service or access to any solution. So this is what we mean. So there can be so many other examples in the same way. So hence, what we are trying to say is that you need to know the entire chain of your application before you start with solving the issues. Otherwise, it is not possible. In the same way, if you are taking a very, very small application which is used by only 100 users of your institute, then you may not require such a very large system of security, because the probability that will try to break is much, much less. The rigorous proofs of security are in cryptography. what we say is that we are doing this task based on what is called as random oracle model. So to explain you in lay terms, the thing is as follows. You assume that there is a black box. That is nothing but your algorithm for cryptographic algorithm. So which takes as input your plain text and key and gives an output ciphertext. Now, any person, the adversary or a legitimate user, can get access to this black box and he can get the output if he is using your system. Now the question is that, is it possible for me to give an input and say what is the output? For example, I'll give my input as bit 1, and can I say with probability 1 whether the output is 1 or 0? In the same way, if I give it to the same black box, the input is 0. And can I say with probability 1 is the output is 0 or 1? That is the question what I need to answer. So now for a better system and to claim that your algorithm or cryptographic system is secure, the probability should be equal to 0.5. That means to say whether given an input 1 with a key k, what is the probability that adversary will be able to say output is 0 or 1 should be equiprobable. That means to say 0.5. If suppose now the adversary is able to say that output is 1 with probability 0.6, then your system is not at all secure. This is how we prove. So there are ways and means of formal proofs, so which I am not going to discuss, which are beyond the scope. So it requires higher ways of understanding of these solutions. So as a layman, if you understand that there is something called as random oracle model, which will do this task of proving it. That means to say, when you design a cryptographic system, you should also give a random oracle model and prove that probability that an adversary will be able to get the plain text is equal to negligible. That's what you are supposed to give. If you prove that, then your system is secure. If it is not negligible as defined in the beginning, then your system is insecure. Okay. So now on scientifically founding information security, if you go, we are saying founding information security on complexity theory, right? It is based on complexity theory. Perfectness is infinite time secrecy. However, it is enough to keep a message secure for very long time, but finite time. So what do we mean by saying this? See, when we say that my password has to be secure or perfectly secure, what I mean by saying is that my password must die with myself. It should never be derived and known by anybody, anytime, and it should die with myself. So it should not be. So now, how to achieve this? If it is achieved, then it is perfectness. Because in most of the cases, if you see now the current day situation, most of us are using Gmail, which means to say that Google knows your password and my password. They can give me my password within no time, and same thing is true with others. So now there is no perfectness in my secrecy at all as far as my password is concerned. But if we are doing something else, if we are using some key for encryption, that means to say that you are signing a contract in the current scenario in the digital form because of pandemic, then you want your keys should be very, very secure because you are digitally signing a contract. Then if it is not achieving this perfectness in infinite time secrecy, then the other party may change the contract and which may write that entire property of yours belongs to them, and it bears your signature, which is serious trouble. This is what we mean by doing this. So now what we are saying is that everybody's computing power is bounded by a polynomial is the assumption we are making, including the adversaries, including the users and anybody else. So taken such an assumption, when we design a system, we want to see that it is infeasible for anybody to break your crypto system in polynomial time. For example, if you are encrypting using a symmetric crypto system, you have chosen a 128-bit key, let us assume. So number of possible keys are 2 raised to the power 128. And if any adversary tries to do this, he has to generate all these keys and do the decryption. So now we can make a very crude calculation. Let us assume that he will take for generation of one key and decryption 1 second. And so 2 raised to the power 128 seconds are required for him to try and get your key. So 2 raised to the 128 is so many thousands of hours. So now what we need to do is that the security is cat and mouse race. You have an adversary and you have the genuine users. So as a genuine user, you want to perform the task very, very fast. As an adversary, for the adversary, you want to make this work as hard as possible. So now you know that if the adversary to generate 2 raised to the power 126 keys and encryption uses one system, he requires 2 raised to the power 128 seconds. Now what he does is he will put together around 1000 computers by using some bot, and these computers can do this task. Instead of 2 raised to the power 128 seconds, it will do in the task of 2 raised to the power maybe 20 seconds. So now what has happened? To get your key, he has reduced his time from 2 raised to the power 128 seconds to 2 raised to the power 20, and 2 to the power 20 is not at all a larger value. Hence, the adversary will be able to get your key and break your crypto system in no time. So now what you need to do to overcome this is you need to change the key for each session instead of repeating the same key. So what do I mean by saying? Today, if you are using this session and you are using a symmetric key, that key dies once the session expires. For example, if you take a real life example, if you take any banking transaction, if you are inactive for more time, the online internet site of bank automatically does the task of disconnecting you. That means your session expires after some time, very quickly. They will not give you much time. What the reason behind that is this only, because it uses a session key for the secure communication between you and the server. If suppose if there is a man in the middle who is trying to learn your session key and hijack your session and do the task of bypassing you and making a transaction, he should not be able to do it. So what does this techniques do is banks, they will do the task of you are expiring the session as soon as possible if there is no activity found from the server. So hence, what we are doing is now, instead of very, very large key, we will use the small key, fine, but we are making an estimation, which is a realistic estimation that adversary will not be able to get the key if you change the key within this much time, and you will keep on doing it. So is it good that we will change the key? Yes or no is the next question. It is yes, because we do not have dearth of keys. If you're assuming 128 bit key, you can have 2 raised to the power 128 keys, which is very, very, very large number. So I need not worry. I need not think that the keys will expire. So I don't have an issue. So the examples, as you see here, we have the defilement key exchange, RSA, message authentication codes, collision resistant hashing, oblivious transfer, bit commitment, zero knowledge proofs, pseudo random generators, advanced encryption standard, etc. This is what I was discussing. All cases we are doing based on these things. The next assumption is the context consists of huge network of nodes, and it may be assumed that not all the network is simultaneously accessible to the adversary. This is the assumption we are making if we are doing this task. Now, examples for this are perfect secret sharing, perfectly secure distributed communication, then perfectly secure multi-party computation, and threshold cryptography. So people need not worry, because we have different mechanisms of perfect secret sharing as proposed by Shamir and others. Then how to do perfectly secure distributed communication also, because current situation, the entire mechanism of computation has changed. We are doing the distributed computation or computation over the cloud, computation over a grid, so and so forth. So wherein we require this security in a distributed environment. And also, we can also do the task of multi-party computation. Then we need to put in place ways and mechanisms for secure multi-party computation. Then we have threshold cryptography, wherein we share the keys or secrets using some mechanism as proposed by Shamir. Then we are achieving the security as required. So the founding information security on uncertainty theory. So secure key establishment is possible over a noisy channel, though impossible in a noiseless channel, because this is what we discussed in the beginning as far as your uh, establishing a secure key between Alice and Bob using the Feldman key exchange. So over a noiseless channel, it is impossible. Over a noisy channel, it is possible. And other examples are Wiener's protocol, information theoretic cryptography, then oblivious transfer over noisy channels. Then everybody knows this, the information theory started from Shannon in 1964 based on his paper. And he also defined what is meant by perfect secrecy. And it is something like this: a crypto system with the size of key is equal to size of the ciphertext, which is equal to size of the plain text. The crypto system has perfect secrecy if and only if each key is used with equal probability. For every plain text X and ciphertext Y, there is a unique key K such that EK of X is equal to Y. So now what we are saying, my key size must be equal to the size of the plain text, and my ciphertext should be also equal to the size of the key. Very simple. Say we have in current day systems wherein we have algorithms which are not of fixed size ciphertext, and some are of fixed size ciphertext. That means to say, if I give an input message M, let us say 1 MB, some algorithm will do the task of encryption where the output ciphertext is also exactly 1 MB. So that means to say both the things, that is a fixed length. Now there is no variation. There can be other algorithms which do this task given in 1 MB plain text. The after encryption ciphertext message size is much smaller than 1 MB, wherein you have a different mechanism. So all these things, when you have, which will reveal some information to the adversary. If the key size is equal to the ciphertext size, which is equal to plain text, and other condition is that key is only used once, no more than that. If that is the case, there is no way that as an adversary, you will be able to learn from the past information or past knowledge regarding the cipher, how does it perform. So hence, it is one and only once you have used the key, and no more than that you are going to use it. Hence, if at all you have to derive anything, is only by means of brute force. That means to say, you have to generate all possible keys and find the plain text from the ciphertext what is available. So which is always possible in any crypto system. That means to say, given any algorithm, brute force attack is always going to work, wherein you try all possible cases. But as a cryptographer or as a cryptanalyst, our goal is to see that how can we reduce this cost of brute force attack by not using all the keys or all mechanisms, rather with a small percentage of effort can we break the crypto system. So which should not happen. So the next thing is founding information security on quantum theory. Right now we have, if we say very simple things, is that initially we had what is called as Caesar cipher. Then we designed what is called as substitution ciphers, that is monoalphabetic cipher or polyalphabetic cipher. Then we had shifting ciphers. Then from there onwards, we went on to design different polyalphabetic ciphers. Then there came the algorithm of data encryption standard then it is proved that DS is not for what is called as the AES advanced encryption standard as far as symmetric keys are concerned. Again, in the symmetric or asymmetric, the crypto system can be based on stream cipher based or block cipher based. In case of stream cipher, we are considering either a bit or a byte as one entity for the encryption. And when it goes for the block, you are defining the block size of the input as an input to the cipher. So a number of operations required in stream cipher are equal to the size of the stream based on how you define it, either 1 byte or 1 bit. And if you take the number of encryptions required in case of the block cipher is equal to number of blocks in the input plain text. So which computationally the block cipher is advantageous for us because number of computations required to be performed by us is much lesser. And if you take the stream cipher, it is very, very large. Then the other issue is that if you are using the block cipher and using the same key, what can happen is you have two blocks which are equal. The block B1, let us assume that B1 is equal to B10 and you are encrypting using the same key. As an adversary, when you capture this ciphertext, both the ciphertext will be equal. So as an adversary, you will come to know that block 1 plain text is equal to block 10 plain text, which is now a serious security issue because your algorithm should not reveal any information regarding what the plain text is. Now what it has said, indirectly, your block 1 and block 10 are equal. That means to say that now the adversary has learnt more information than what he is supposed to learn, which should not happen. So hence it leads to easier attacks. So we have to think about this. Then if we, so all these symmetric key algorithms, the security of your system is equal to security of the key. That is the, what we call it as Kirchhoff's law. It says that security of your cipher is equal to security of the key. In case of symmetric crypto systems, we do not have large size keys, we have small size keys. But what we do is that we try to perform diffusion and confusion using the algorithm to see that we are able to have much more difficulty for the adversary to get the key, which is achieved again by means of frequently changing the key for different sessions, so that even though adversary tries to get the key, it is of no use because you are never going to use that key again. Hence we will overcome that. Now other stream of cryptography is public key cryptography. In this case, what we are saying is that we have a public key and a private key pair. For example, in case of RSA, then the public key is used by the party who intends to communicate with the other party. So he will use that, encrypt it and send it to the other party whose public key it is. So intended user will decrypt it using private key and he'll perform the task. It is based on the assumption that breaking the integer factorization is hard. If somebody proves that P is equal to NP, then integer factorization can be done in polytime. If that is the case, then we are going to lose the entire RSA and security. Then the other issue is that the recent past, the things have been developed in the area of quantum cryptography. So now we are using quantum cryptography. Using quantum cryptography, people have developed key exchange protocols, which is much secure than the Feynman key exchange protocols. Let us not go into very detail of this because some mathematics has to be studied, which I cannot cover now. So what we are going to do is very simply two conjugate bases are used, say B1 and B2. Yes, chooses a random base based on bit to send. It sends a qubit prepared in the corresponding state. Now R measures the qubit received with the random base. If the base is different from what S is used, the bit is lost. Else R measures the actual bit. This process is repeated for all the bits yes and r publicly. All the yes and r publicly compare their respective bases and discard all those bits where their bases were different. The bases are same for nearly half the number of bits. S and R now check whether adversary has intercepted any of the bits by comparing certain subset of the remaining bit strings. If more than p bits differ, they abort the key and repeat the process. This is how they do, because once somebody reads a bit in case of your quantum cryptography, its value changes. And we are saying that if they have used a different base, it changes to something else and bit is lost. So this is not supposed to happen. In future, what we need to do is, now we are going to have these things. So adversity, exactness, interdisciplinarity, overhead, and unification. Because now currently what we are saying is that how to use this cryptography for the future demands and also future challenges. So as far as adversity is concerned, as adversity increases, security reduces due to possibility of multiple attack. And also the principle of adversarial interference, that is, the adversaries may destructively interfere with each other, thereby increasing the security. So what does this mean? What we are saying is that if, for example, to name the attack is advanced persistent threat. So advanced persistent threats are 100% successful, right? So if you want to attack somebody, by hook or crook, you are going to attack them. There is no question of failure. Now, if you want to achieve that, you may need to use large resources. Most of the time, these advanced persistent threat attacks are performed by the state holders. That means to say that, for example, the government of a country will support it. For example, China or Russia. So their task is to attack certain organizations of the world to get an information. So they provide sufficient resources and it is going to perform this attack and they will be successful. Hence, there is no way that the other country can mitigate such attacks, because they are going to see that what are all means they will be successful and they will persist on performing that attack. That's why advanced persistent attack, and they will be 100% successful. They may use different social mechanisms, socio-economic mechanisms, or psychological mechanisms to achieve these objectives. So we need not go in detail. How do we do it? Now, what the other thing can happen if it is a blessing in disguise is that there are many adversaries who are coming together or they are disjointly attacking a entity. So now if we do this task, then it may so happen that it will interfere with the attack and they may increase the security of your system. For example, if you have noisy channels, this is the case, and then we have designed what is called as randomized algorithms. So what we are going to do is that the simplest example is the randomized quicksort, because quicksort takes O of n log n time. You can still reduce the time using randomized quicksort, wherein you have a random pivot you select based on which you do the task of doing this sorting, and which is much faster than your quicksort algorithm. Then the next thing is the plethora of uncertainties, that is delays, faults, network configuration, workload. All these are also an uncertainty. You may have a very good device and very computationally high powerful computer, but you have appointed a person, one who does not know how to do the administration of such a system, and whatever investment you have done in making your infrastructure and security, they will become null and void because of this one person. So that is the issue. Now the exactness. Proofs from scratch are very much important in case of our cryptography. So there is no scope for conjectures because somebody can disprove them. So which is a leap in mathematics. Now the other thing is, what about physical exactness? That is, quantum one-way functions are different from one-way functions, likely to be more powerful. That is the likely to be, that's what we are assuming. So how can we do this task of physical exactness? One-way functions, as far as cryptography is concerned, using mathematics are different, but if you are going for the quantum one-way function, they will be totally different from this. Then interdisciplinarity. Cryptography benefits from and is beneficial to coding theory, then distributed computing, then mathematics, algorithms, and quantum mechanics. So how is it? Let us see. So now the Shannon's information theory and coding, Shannon proposed, right? Shannon said that to do the task, again, the digital communication, we have to have the Nyquist criteria, because 2 times the frequency we have to sample it and send it. Then the Shannon also proposed the different error controlling codes or error control coding for the task of communication. And we proved that a key can be shared between 2 entities even though the communication has noise or error. Using the discrete log problem, we proved that we can share between 2 entities a key securely, whatever it may be the scenario, which is an advantage to coding theory. Then the next thing is that in case of distributed computing, we have proposed, based on threshold cryptography, techniques to perform distributed computing securely. So without this threshold cryptography, distributed computing securely is not possible. Then we have also contributed to mathematics. That means to say that we have come up with one-way functions, which were the mathematician thought that they were of no use. Using cryptography, we proved that just the one-way functions are very, very important, and research in one-way functions will lead to much, much better secure environment and world if we do it. So mathematics, so the research in one-way functions has increased exponentially because of that. So the cryptographers or computer scientists are contributing to the development of mathematics. In the same way, if you go to the prime numbers, yes, the computer scientists have contributed largely to the primality test. For example, our Manindra Agarwal has proposed primes in P, which is an algorithm to check whether a number is prime in polytime. Hence, there are very large contributions from cryptography to mathematics. In the same way, mathematics also will help us because of number theory. The number theory is the most oldest branch of mathematics, which has helped us in designing so many cryptographic algorithms. Next, going to the algorithms, because we study theoretically most of the issues pertaining to decision problems, which belong to the class P or NP complete or NP hard. Now we have got a real-time application of those. What we are saying is that, yes, if you are able to prove something is NP complete, a decision problem, then I may have a public key crypto system based on that, which may be secure. So for example, the integer factorization is assumed to be hard and it belongs to the class NP complete. Then we took that as a mechanism to design the RSA algorithm. Then the algorithms, now in some of the cases we want to break the crypto system, then I need to find a way how to do it. Then what we need is that the randomization algorithms. The randomization algorithms help us in saying that the upper limit for computation required for such a limited computation is only this. So I can do a task of designing a randomized algorithm and break a crypto system. Then the quantum mechanics exists, yes, from Einstein proposed, so which is still existing. So what we are trying to do is that design a quantum computer so that we can make our life much better. Other way around, the cryptography is adding to the development of quantum computer. Also, it is helping them to design new algorithms in the area of quantum mechanics for the communication. So hence, the cryptography is benefiting from all these areas, and also all these areas are getting benefit from cryptography. So any area, if there is any development which may be helpful for cryptography, and other way around, if we develop something in cryptography, it is beneficial to the other subjects what we have mentioned. Okay, now uh, maybe I will give after 5 minutes time for question and answer. By the time I'll be finishing. So the is security and overhead is the question, because what we have discussed is that we want to make our system secure. So is security and overhead? The current answer is yes. Expected answer is not always. And futuristic answer is no, it is a part of mainstream work. So what do we mean by saying this? So what we are saying is that security should be part and parcel of life anywhere you go. So it should not be an add-on. So like what we used to do earlier. So once it becomes a part and parcel of any design, then our life becomes much better. We will be very much secure than what we are today. Then the next thing, analysis. Why remember and moreover test auxiliary knowledge which is of this is better. So for example, do you remember your password? Do you remember your job work to be done, or do you remember the relevant tools and techniques? So what we are saying is that till now we went through so many issues of cryptography, and after knowing what good I can do using cryptography and by what bad I can do using the other things. So now the question is, can we need to know the password at all? Because if I am not at all a threat to a system, why do we need to know the password? Because the system should simply permit me to access it, right? So we are providing security because something is a threat to the system. If there is no threat, we don't need to have security. So what we need to know? So if I remember what is my work, which is more than enough, and if I also remember the tools and techniques what I need to know to perform my job, that is more than sufficient. The remembering a password is an additional burden for me, because I assume that I am not a threat to the system. So what we need in the future is such a system. So now towards unification, getting machines to do your task, that is hardware, the microprocessors, architecture, organization, then systems, the operating systems, database systems and compilers. Then you have computational thinking, data structures, algorithms, artificial intelligence, then interfaces, for example, computer networks, GUI, human computer interaction. So now finally, where is security? Currently, it is added post hoc everywhere. Are we missing something? Yes. Attacks across modules. So I'll stop here. Thank you very much. Now the forum is open for any questions from any participant.
Participants, please unmute yourself and you can ask questions.
Looks like there are no questions. The participants, please ask the doubts which may be clarified now.
So one question was there, visual cryptography scheme.
Okay.
So can you explain?
Okay. Okay. Now, see, when if you take an image, in case of all these things, what we have discussed, what we are assuming is that we are taking some input, plain text, and doing the task of encryption and decryption. So now, how do we go about doing the same thing for an image? Is the question. So now, if we are having an image, if we apply whether symmetric or asymmetric cryptography, amount of computations what we need to do is very, very large. Hence, it becomes very, very costly affair. So can't we do using very, very simple techniques the same issue? Okay. So to do this, now Adi Shamir proposed what is called as visual cryptography, which is based on threshold cryptography, Tkmce. So what we do is that, let us take a simple case of an image pixel. I have only a black and white image. So what we do is that if you have a black and white image, you have white pixel and black pixel. Now you will generate the share for this image in the following. That means to say, if you have the white pixel, you are going to have 1 cross 2 image as its share for 1. That means to say, the shares size is going to increase than the original image. So now what I'm going to represent, if I generate the shares, if I overlap them one above the other like a transparency, it must give me the original image. That is my objective. So it does not require much computation. So what do I do is that, now if white pixel at the receiver, when they overlap with the number of shares what we have generated, now how many shares shall we generate is the first question what we need to answer. Let us assume that we are only going to consider 2 shares generation. So I have for one participant the one share, the other participant the other, and if they put together both the shares, overlap it, they'll get the original. Now the thing is, now I have the, for white pixel, for the shares I have the chances of I will say 2 pixels as white white in the horizontal direction, or in the vertical direction white white 2. And for the black pixel, I'll say that amongst that, now I have to generate 2 shares. When I overlap them, it should give you black. That means to say that for one party, I have to give 1 white, 1 black pixel, and the other party, the first one should be black, other should be white. That is one possibility. And the other possibility is that first one will get a share wherein the first pixel is black, other is white, and the next pixel, it has white and black. So now these are the combinations. So what I'm trying to say is that you are going to pick 2 of them. That means to say, you are generating a share, white pixel will be represented as white, black pixel as 50% black and 50% white, but different orientation. So for the first share, you will do one orientation. If you take, for the second share, you will take the next orientation. Now what is going to happen when you overlap these 2 pixels, black and white, the black will appear white, will always be white. Now what is going to happen? The size of your transferred image is going to increase because of this. And the next thing is that you may have different frequencies of white and black. All those cannot be taken care of. So hence what it happens, 50% of the contrast of the original image will get reduced. So the reconstructed image will only be of 50% quality. So this is the very, very simple mechanism of doing visual cryptography, as we do in case of transparencies. So there are so many others, so which I will not go through. We can extend this scheme for the color images. We can also have the same size shares generation using different techniques. And also we can have block-based progressive visual secret sharing mechanisms. So many are there, so which are beyond the scope. Any other questions?
So I think, sir, there are no more questions. So,
Okay, sir. If there are no more questions, I would like to thank Professor K.E. Robi Roy for giving me this opportunity to interact with the participants of Atal program. Also, I would like to thank the TKM College of Engineering for giving me an opportunity to give a lecture on Introduction to Cryptography. Thank you very much, sir.
thank you, sir. So on behalf of Department of Mechanical Engineering, Teaching College of Engineering, and on my own behalf, I sincerely thank for all the efforts and for wonderful session you had here. Thanks for accepting our invitation also. So thank you, sir. Thank you so much for being here with us for this session. Thank you, sir.
Thank you. So I will disconnect.
Sure. Okay, sir.
Okay. Thank
Thank
you.
you.
Thank you very much. Bye.